Hello, my name is Elee, and in this video I will be going over assignment 2 for Dr. Lawrence's ChE 3102 class. So the objectives for this assignment were to first solve a 1D transient heat transfer problem using Python, graph our results on a temperature versus time plot, and then finally we want to explain what the stability criteria would look like for the 2D and 3D transient heat transfer problems. So this is our problem statement for the 1D problem. It says a brick wall with a thickness of 0.5 meters is initially at a uniform temperature of 300 Kelvin. Determine the length of time required for its center to reach 425 Kelvin if its surfaces are raised to and maintained at 425 and 600 Kelvin respectively. So I first want to kind of help visualize the problem. This is the brick wall right here, these solid lines. And so on the left, we have our maintained temperature of 425 degrees Kelvin. And then on the right, we have 600 Kelvin where it's maintained at. And we have our length of our wall at 0.5 meters. And then we have our center wall initially at a temperature of 300 Kelvin. And the way this works is, as time goes on, these temperatures are going to change rapidly due to these maintained sidewalls. So our overall goal is to find the amount of time it takes for the center of the wall to reach 425 Kelvin. So these are the equations that we will be using to help solve the problem. We can first start with rearranging the heat equation to get our first one here. And I-1 accounts for the left side of the wall, while I+1 accounts for the right side of the wall. And our overall goal is to find the temperature at the center of the wall after a certain amount of time. So we can rearrange this equation to this one right here. And to help further simplify the equation, we can use the stability criteria listed below. Since it's a 1D problem, we know that it has to be less than or equal to 1/2. And if we know if it is not small enough, solutions may oscillate and diverge from the actual solution. And also another important thing about it being 1/2 is it allows us to simplify the equation by getting rid of this part, so all we are left with is this side right here. So the first thing I wanted to do in my code was obviously define the variables that I wanted to use. So we can start with our values that we were given in the problem, such as alpha, the initial temperature at the center, and then the temperature of the left side and the right side. We can also use our delta x as distance as 0.25. That is the distance from one side of the wall to the center. We can then use values t plus val and t minus val to help store our values that we will use in our loops and arrays later on. And this is also the case for our total time. This will be our time counter in a sense in order to see how long it takes for the center of the wall to heat up, as well as this I step that will be used as another counter in our while loop. So we then want to define some arrays. These first two arrays right here will hold our t minus and our t plus values that will be used in the loop. This array right here will hold our time values that will be used when we plot our results later on. And this temperature array will be used to hold our temperature values that will be used to be used when we graph our results at the end. This is the while loop I use to help solve the problem. So we can start by setting our bounds, I guess, for the problem. We know we are trying to find it when the temperature of the center reaches 425, so we want to execute the loop until we get to that temperature. We then initialize the sides of our wall to be maintained at those two temperatures right there, since that was given in the problem. We can then use this for loop to go through it 5 times. It says 4 because Python is indexed. It starts at 0, so it will go through this 5 times, and then we will get the iterations for our distances, and then we will add them to these lists right here. Then we can get our temperature values for the t minus and t plus right here by using the last value we calculated. That's what the -1 is there for. We can plug these into this temperature equation right here, which does not account for the stability criteria being 1/2. We can then add 1 second to our time, our total time when it goes back through, and then we can put our store time values right here. We are dividing by 3600 to put it into hours to make the graph look better when we get there. And then we will once again use our temperature array to hold all the temperature values that we calculate. So these are our results that we ended up getting from the loop that we did. As you can see, our total time that we calculated was approximately 16.32 hours, and this is the trend that I saw as I graphed our results. So the stability criteria for 2D and 3D problems, as you can see, it is not 1/2 because you have to account for more directions for it to move in and more opportunities for it to become unstable and iterate unexpectedly. So that's why in 2D, I found that the stability criteria had to be less than or equal to 1/4. And for 3D, the stability criteria had to be less than or equal to 1/8. All right, that's all I had. Thank you for listening to my presentation.